Yeah, so you see the assignment problem. I'm reminding you what it is and what it's trying to achieve. In the assignment problem, you have two groups and you try to find a good match between them. The groups are the same size. So the classic application is a group of workers that needs to be assigned to a group of jobs. Same number of workers and jobs. This is why this problem is called balanced. To remind you of the balanced transportation problem. In this example, you have three programmers that can be assigned to three programming jobs. What's unique about the assignment is that each worker can do exactly one job, and each job needs exactly one worker. So it's one-on-one. Modifications of these are common, and I'll mention one or two of those. And the numbers that you see inside this matrix are the times it takes for each worker to complete a job. Why are these times different? Because workers have different expertise. Because workers are not the same, and some are faster and some are slower. So management is estimating the time it takes for each worker to finish each job. And as you see from here, that each worker can work on each job, but it's preferred to give John work on job 3 and not on job 2. So the problem of the assignment is how to assign workers to jobs such that the total time of completion all the 3 jobs is minimized. Maybe these workers are getting paid by the hour. So, and this is in hours. So management tried to minimize the total hours, maybe. There are other applications in which these are costs and not times. Same idea. So this is, in general, the assignment problem. I just want you to understand, this is a little tiny problem. With 3 by 3, you don't need a model. You try several combinations and you find the optimal solution. We are talking with large groups of workers and jobs in which the number of combinations of who goes where is humongous. It can be millions. What if you have 30 workers and 15 jobs? So now only 15 workers are needed. Which 15 you are going to give up on? And those who are left are going to be assigned. How? Now it's 15 by 15, it's 225 workers, combinations. So those problems explode very, very, very fast. Good algorithms to solve them are needed, and they exist. And we'll talk about it very, very generally, because it's not a course about algorithms. It's a course about knowing the application. So this problem can be described in something that will remind you of the transportation problem. Indeed, when we go to this mathematical programming of this model, you will see that it reminds us of what we saw in the transportation. On the left, there are 3 nodes that represent 3 workers. So John, Marjorie, and Ronaldo. On the right, you have 3 jobs. The arcs here represents possible assignments. Each one of the workers can be assigned 1 time out of the 3. Therefore, you see the number 1 here because John can offer only 1 service. This is the supply. Then on the right, you see only once, because each job requires 1 service. That's the demand. You see the equivalence between this and transportation. It's transportation in which supplies and demands all are equal to 1. If it is transportation, we can apply the linear programming of the transportation model and put ones on the supplies and one on the demands, and we are done. And that's what we are about to do. On the left, decision variables are just like in transportation. They have two indices, I and J. I represent the worker, J represents the job. But the variables are unique. Not as opposed to what the variables were in transportation, in which they represented how many units you ship from source I to destination J, and these shipments could be any value within the capacity and the demand, any value. In here, we assign only the values 0 or 1 to Xij. 1 when a person I is assigned to job J, and 0 when it is not. There is nothing in between. It cannot be half an assignment. These kind of variables are called binary. We saw binary variable in multiple regression on the dummy variables. They were binary. But here, these are decision variables. And so we will have to find the best selection of ones for Xij, such that a person is selected once and a job is selected once. And this is where the constraints come from, but let's look at the objective first. 100 is the number of hours that John will do job number 1. If John is assigned to job number 1, X11 will get the value 1. So 100 times 1 give you 100, which is added to the total time. If John is not assigned to job 1, X11 will be 0, and then there will be no addition of time. And this is how all the objective function is now formed, with the coefficients times the binary variables. Constraints. First of all, the workers, which I make an equivalence between it and the supply constraints. Workers can provide services, so they are the supply constraint. John can be assigned once by the requirement. So if you take the binary variable and add them and make it equal to 1, only one of them will be equal to 1. Remember, binary. It's either 0 or 1, each one of them. So if the sum is 1, exactly one variable here is going to be 1, and the other 2 equal to 0. This is done to John, and then Marjorie and Ronaldo. These are the supply constraints. So I'll keep asking you from time to time if it's clear. So I'm asking now, is it clear? Okay. Now we go to the demand constraints, and this is the project. They demand workers to serve there. A job needs exactly one programmer. So let's add all the variables that go into job 1. You see 1, 1, and 2, 1, and 3, 1. And limit it to 1. This makes it necessary that exactly one of those will be 1, the rest are 0, and this job is getting exactly 1 worker. So is done to the other 2 jobs. Okay? Now, if you look at this model and this objective, it is a balanced transportation problem. That's exactly what the transportation was when all the constraints were equal to. That's the situation here. So as far as the algorithm that solves it, you would just go to Excel and we'll do it and get this optimal solution. So now about this optimal solution, I have one word. You know what? No, let me do the other model first, and then I'll talk about that. The other problem will make the problem unbalanced. Why? Because Jalila is a fourth programmer. She was found to be available like the first three, and management want her to be a candidate to get the project, a project, just as the other three. But now we will have a supply of 4 programmers and the demand remains 3. This is what makes the problem unbalanced. It's clear that when we are done with solving this problem, one of the programmer will remain unassigned and the other 3 will do the job. The only question is which one. So we'll have to add Jalila to the model, and I added it here. This is the objective function. 3 new decision variables, x4 for Jalila, 1, x4 2, and x4 3. Those numbers of 105, 98, and 90 are mentioned here. This is how long it takes her to complete each project alone. And so I added her to the previous function, and I have a longer objective function now with 12 variables. It was 9 before. Now we go to the constraints again. Now we cannot force all the 4 workers work because we have only 3 jobs. So we must allow one of them to not be assigned. We don't know who at the beginning. So we just allow it, let the model decide based on total time minimizations of those who are assigned. So the constraints on John are just changing from equal to 1 to less than or equal to 1, just in case John is the one that is not going to be assigned. And so are the other 3, and I say 3 because the constraint for Jalila was added here. See, this is John, and this is Marjorie, and Ronaldo, and Jalila. I added a 4th constraint of her offering services that may not be needed, so that's why less than or equal to 1. And the model will decide where the optimal solution goes, which one of the 4 is going to be picked up. On the project side, that's the jobs, there is no difference other than adding Jalila to each constraint. Each job now must include her, but each job still need to be done, so therefore equal to 1 on these 3. We are done. We have a linear programming for an unbalanced problem when the number of jobs exceeds the number of workers exceeds the number of jobs. And the other side of the coin is when you have more jobs than workers. Then for sure, not all the jobs will be done, but all the workers will be assigned. So you just switch the constraints, and well, I will not go there, but it's very similar to the treatment that I gave there. You have only 3 workers and 4 jobs, so you have to adjust the equality and the inequality in a similar manner to what we have just done. Now, a word about these variables that are binary. This includes both cases here. It includes every network in general and every transportation and assignment being networks in particular. If you take a linear programming model, say a larger model with hundreds of variables and thousands of constraints, all linear program. I was working on such a model a few months ago. And it has like 600 constraints and 900 variables, all binary. So when you try to solve such a model and you tell solver all of them are binary, first of all, it will check to see how many variables there are. My model could not be solved by solver. I needed to go to another software. But A model that solver can solve as far as the size goes, if you add a restriction that tells solver that only binary variables can be used, which means only values of 0 and 1, solver will find it very hard with simplex to solve and give you a solution in real time. My model, that was really large, was working for a few hours to get the solution. And it was a good software, better than solver. It was binary, that's why. When you add the requirement of binary, you are making it hard on the algorithm to give you an optimal solution. Transportation and assignment are notoriously large problems. You need special algorithms to solve them. If you could avoid telling the algorithm that these variables are binary and still get an optimal solution by the algorithm that is all binary, then you're in a good shape. The reason? Even solver will give you an optimal solution very fast once the variables are not of the binary type. Fortunately, problems like this, you do not have to report to solver that you requires binary variables, because solver will come back to you and tell you the optimal solution is binary whether you like it or not. So you should be very happy. The reason is I get an optimal binary solution without me asking it very fast. So bottom line, we will not talk about this binary anymore, because we will not have to report them being binary to solver. Solver will give you them as binary optimal, and it will be extremely fast. So that's what I wanted you to know about this binary thing. And now it's time to go to Excel and practice these examples. I think just a moment. Here, okay. Here is the example that you already have, that I sent to you again today, because I added a few items in other tabs here that were not there before, that I want you to take a look at. The problem I'm referring to is this one. And this is exactly the problem that we've seen just now. So you see a linear programming problem of that model that includes 3 programmers and 3 jobs. All the constraints are equal to 1 because the problem is balanced. And now focus on those values here. These are the objective coefficients, which are the times to finish each project by each programmer. These were defined as the decision variables in solver. And now the constraints. So you have programmer number 1 is assigned ones. So you add the variables of this programmer, you see x11, 12, and 13. Therefore 111 are equal to 1. Programmer number 2 and number 3. Okay. Now for the jobs, you have a worker that is working on job 1, another one on job 1, a third one on job 1. The sum has to be equal to 1. The sum will be calculated here. And then the other 2 jobs, the same thing. The sum product. This one will calculate the total time. So it will, this is a given solution that I solved before. So for this particular solution, you'll get 100 times 0 plus 102 times 0, no assignment. But worker number 1 is assigned to job 3, so you have a 1 here. So therefore 95. plus 97 plus 87 gives you 279. So this is the first sum product. Actually, this is the optimal solution, only that I'll go there and perform it. Then you copy this in here, see? And these are the sum products. You must get one here and here and here, and each left-hand side must be equal to 1, because you have 1, 1 in each row, and then 1, 1 in each column, as you will see in a few minutes. And then you solve the problem. So the optimal solution that we have here might not be, yeah, it's not for this model. So let me delete it and redo it. Delete and delete. So first I enter the objective function, it's here. Then it's minimized with variables. The variables are selected here. Okay. And the constraints. Do you notice that all of them are equal to, so I can select all of them in one hit, and I don't have to separate it to supply and demand, which is what I'll do in the next model. So here I just, for convenience, select all of them, make them equal to, see, and select them again. And I have all the 6 constraints here: simplex, non-negativity, solve. As I said, this is the optimal assignment. And this is how much time you need to finish all the projects. Now, what happens if there is an additional worker, Jalila? I did not include her in the first model. I am going to include her in the next model. You see, programmer number 4 is our lady Jalila. So what happens here? First of all, I have to add variables that indicate her assignments. I added 3 new variables for each project, and 4 stands for Jalila on the right-hand side of the others. And put the times here. Okay. Then I added a constraint that has to do with her assignment. So you have under the correct column 1 and 1 and 1, which continues the structure that you had here. And then the projects remain 3 of them, but you can assign Jalila in them too. So I added her variable to each constraint and keep it equal to 1. What I need to correct is now this objective function that cannot stop at x33, so I extended it, you see, to column M. And then did some product, so now the constraints also include the 3 new columns. For example, this one, see? It includes everything all the way to M. Now, when I enter it in Solver, I have to separate between those constraints and those constraints. And first of all, the objective is moving here. Here. The variables need to be extended. And so here's a new line of variables. Okay. On the constraint side, I'll delete this one and add new sets of constraints. I have to separate because the signs are not the same now. For the supply, I'll write that 1, 2, 3, and 4 is less than or equal to 1, 2, 3, and 4. Oh, wait a minute. Again. 1, 2, 3, 4 is less than or equal to, click. That's what I missed. 1, 2, 3, and 4. Now we are good. And then I'm adding 1, 2, 3, change it to equal to, and then enter the right-hand side. That's it. Solving the problem is going to give us a different assignment plan in which Jalila is selected. Well, she was not available before, but now that she is selected, and guess what? Worker number 1 has no assignment. And the total time is now lower than before by 5 hours. Here against this one. So that's how you treat an unbalanced linear programming problem. And I want now to go to another way of formulating such a problem with and without Jalila. So first of all, without her. Okay. You use a rectangular format instead of one-line variables. Here you put it in a rectangle, like a matrix. Can somebody tell me, did I mention it to you last time? Did we do it last time? Anybody?
Yeah, we did.
So does it pay to repeat it?
Yes, please.
People are not talking because of what? So, okay, I'll repeat it because it's important. It's good for larger problems where you cannot list all those variables in one line. Imagine a problem that is very moderate in size and it's 12 by 12. It's 144 variables. Imagine this in one screen. It's not going in one screen. But in a table of 12 by 12, it's easily organized on a screen. So I organize the data, the input here, instead of on one line in a table. And then what I'll do, I'll work on the variables as if they were exactly under the same format. For an ease of work here, I will copy and paste and make these cells my decision variables. This is where I'm going to place them instead of this single row. So let's just, I like to make an indication for me and for you that this is where the variables are. Now I work on these variables in creating the constraints. Okay. Okay. Oh, shit. Never mind. So the first constraint has to do with John. John can be either working on job 1 or 2 or 3. This is x11, x12, x13, so I have to add them. And I'll copy it down to the other two constraints. And this means that here is the assignment for Marjorie, and here are the assignment for Ronaldo. These need to be equal to 1. So I'll write, say, 1, 1, 1. This is how I'm going to enter it in Solver. Then here, it will be the job. So it's John to job 1, or Marjorie to job 1, or Ronaldo to job 1. The sum, again, has to be equal to 1. All the three sums need to be equal to 1. So you do equal to, and then you know that you can write the number 1 here and solver will accept it. So if I'm writing all the sums, all of them equal to 1, solver allows that. I don't have to write 1, 1, 1. I don't have to. So now I just need to have the objective function. I'll put it here, time. It's a sum product of the coefficients times the variables and we are ready to go to solver. Is it too fast? Okay. Let me delete what we don't need. And I'm going to enter now the objective function, which is here. Okay, see. Minimized. Variables. Here are my variables. And then I'm adding constraints. 2 sets of constraints because they are separated to supply and demand in the table. Those sums are equal to 1s. Then I'm adding those sums, which is the demand constraints, and I'll write equal to. And now I can either click on the 1 here or can type the number 1. It's allowed in solver. So all the 3 are equal to 1. You can enter it this way. And now I need to solve the problem. Simplex is activated. So I'll solve the problem. And we have a solution. And the total time is 279 as before. And the assignments, let's see. Here we have worker number 1 to job number 3. And here we have, you see, it's easy to read here exactly what the assignments are very easily. Even when this table is very large, like, as I said, 10 by 10, it's just jump to you. You can work now on Jalila added to the picture. You'll have to adjust this model. Okay. Well, you have to correct now what's here. And I need some more room. So let me move it. Okay. Jalila will be here. Okay. These are assignments of the lady called Jalila. They were not included in the previous problem. I'll have to add them the same way I added those Y's here. I'll have to add them. I'll do it when I go to solver, I'll do that. Now, if Jalila is included, then her assignments should be summarized as a sum here. So I'll copy this sum down. It's still 0 because there is no assignment for her here. And I'll leave this one alone because we have to think about it for a second. But she cannot be assigned more than once. So I'll put a 1 here. Okay. Now, how about the jobs? Each job must be done, not over 3 workers, over 4 workers. So the sum that I have here that cover only 3 workers have to be extended by 1 down to 4 workers. So this sum includes Jalila now. I'll copy it here to the other 2 projects. Everything is ready almost because I have to correct now the objective function. Because take a look what it does. It's only including a 3 by 3 matrix, but it has to be 4 by 3. So I'll take this and extend it here to Jalila 2. And then this one extended to Jalila also. Now it's 4 by 3. And I'm done. And we can go to, you may ask, why do you still 279? Because it's still the old solution, not including these 3 cells. So let's see what happens here in Solver. The objective, I kept it the same cell. Variables need to be extended by 1 row. So the variables will be 1, 2, 3, all the way down to Jalila. See? These are the variables. What happens on the constraints on the job side? So we have the sum has moved to row 18, I think. I have to correct it. See, the sum, oh, the sum has moved. So what I see here, I have, it's 16, let's see. Okay, so we are on the right. So this has been updated on its own, and I have already corrected that it includes 4 rows here. No need to correct anything. That's here. Now I go to these constraints. Now, because we have 4 workers and only 3 jobs, I cannot force the model to assign 4 workers. If you do, by the way, it will come back to you immediately and say infeasible solution. You asked me to assign 4 workers to 3 jobs. Impossible. So I have to correct it, and you know how already. I'll write here, just a moment, close, and correct it. I'll write here, less than or equal to, and then I go back to solver, and these constraints here, I'm going to change them. Yeah, this constraint I'm going to change. So this is okay. I have to extend it 1 more row. So it will be 1, 2, 3, and 4. These ones are not equal to, are less than or equal to. So I select less than or equal to. And here I have to correct it to 1, 2, 3, and 4. So I extended the 2 dimensions of the table, and I solve. As you see, Jalila is indeed selected, and John is not, which is, by the way, what we got when we ran this model here. The time is 274, I see. So there is 5 hours of savings. And this way we solve an unbalanced problem on a rectangular form. I would like you to know how to set it up as a linear programming this way and how to set it up as a linear programming that way. Not going to ask you to enter it in Solver and solve it on the left here. Just want to see if I'm asking you that you understand how to set it up on a piece of paper. But I may ask you also to do solve it with Solver on the rectangular because it's much easier to do. So I may ask you show, I call this the assignment table. I call this the assignment linear programming setup. This is the assignment table. In transportation, call it the same names. Transportation table will be the rectangular form, and the transportation linear programming setup is this model that you see on the left for transportation. I'm not going to ask you in the test to solve any linear programming itself by plugging it into Solver. You yourself will need to practice it at home to do sensitivity analysis because you will not get sensitivity results if you don't do Solver before. So I'm not going to test you on how to enter data into Solver. Not going to do it. in this is unique. It's simple, it's fast. And this is, I want you to show that you know how to do, get the solution and demonstrate what your solution is. So, and in any linear programming in the test that you have to set up, not asking you to solve it with solver. I'm not, I never do, not even in the classroom. Because I don't want you to spend the time on plugging numbers on the keyboard and you make mistakes and you don't understand why solver doesn't work. It's not what I'm testing you on. I'm testing you on understanding. And that's why I will not do it in the test also. But when you practice from the book and the book does not give you the solution, you'll have to enter it in solver. So you have to know the sum product and how to enter constraints and then obtain a sensitivity report. All this you have to know how to do at home when you're getting ready. And so I'm not worried, you will know that. I'm just not testing you on that. Okay. This is about what I wanted to do today. There are a few more things in the transportation side that, you know what, I will not do it today. I'll do it in our last meeting, and then I'll do another review problem on some general linear programming plus sensitivity analysis. Now about sensitivity analysis, I sent to you a file, I think on Friday. So like 4 days ago, 5 days ago, that includes several different linear programs. And I also added sensitivity questions of my own and answers. And I want you to take a look at that. Anybody missed that file or you have looked at it? Anyone? I don't see names now. I don't see names because I only see Excel here. Anybody has looked at it already? Guys, don't be late. You are almost too late. You have 1 week. The exam is on Tuesday, 1 o'clock. Did you receive the calendar? I sent you a calendar of all the exams. It was, yeah, last night I think I sent it. Right, last night?
Yeah.
Okay, so you know your exam is in a week. And linear programming, gosh, you have to practice that, guys. Okay, let's talk about that. Let's talk about that. Take like first 10 problems from the book. I didn't cover all of them. You cover them yourself. You have solutions and they are similar to one another, but each one is a different application. And I want you to see different fields that linear programming can touch. It's important. That's to see the exposure. So I would like you to be able to solve them. They are not large problems and are based on what was given in the text itself. So the best preparation now, I think, read the text, chapter 12, and then cover sensitivity analysis also. It's there. Then take the first 10 problems, solve all of them. Some of them we already have done. I remember 5 we did, 6 we did, 12 we did. On transportation, you have enough questions. You have 2 transportation problems here that we didn't touch yet, and you have more transportation problem and assignment you have here in the other file on the review. And if I find something good and I can come up with some interesting application, one of them I'll show to you today, then I want you to work on them. And this is what you should expect in the test. And so, and that's all what I wanted to tell you about the test. And then I want just to finish with another application of assignment. And this is a regular balanced problem. Why do I show it to you then? Because I want you to see that the assignment might have different faces, not necessarily workers that are looking for a job. It's not this match necessarily. So this is an interesting application, which is a real life application. A company that has purchased a huge warehouse and converted it into a plant. A lot of work was done there and architecture was determined already. And so they have now 5 assembly lines. They are producing electrical devices. And they have also 5 inspection centers. Because the production goes like every half an hour, there is a throughput through the assembly lines, put them in bins, and a vehicle is coming and transverse them into the other side of the building to inspection. The inspection is made, and those that are defective are put on the side and thrown out, and the rest are shipped to customers. So, and by the way, this is the simpler version of the problem. The more realistic problem is that the inspection is done, some are thrown out, some are sent back to the assembly line to be reassembled because it can be repaired, and then sent back for inspection. So there is a circle here. And you can solve even this one as an assignment problem, but I keep it simple. You have items being produced in assembly lines and then shipped once to a inspection, and then from the inspection shipped out. Now, in this structure, you have 5 assembly lines and 5 inspection centers. There is specialization here. Each inspection center can inspect certain types of devices. Therefore, each inspection center can work with a single assembly line. And therefore, each assembly line will ship only to a given inspection center. So how do you decide which inspection center will work with which assembly line? By the time it takes to transport it from the production center to the inspection centers. And this traffic in the building might be quite intense. Every half an hour, and there are workers and there are machines, so every half an hour, a vehicle is moving from all the centers to all the centers. And so management has evaluated the cost, that it cost them a year in equivalent time dollars to ship items from assembly to inspection, and it came up with something that exceeds $150,000. And this is even a moderate assumption. So they say, hey, this is not an amount we can live with, we want to save. And why did it come with so much? Because they arbitrarily assigned inspection centers to assembly lines. They say, let's do it in a more scientific manner. They measure the time, and you see it on the left, in minutes that it takes to ship from each assembly line to inspection. I made the inspection as the supply because they provide the service. I made the assembly as the demand because they ask for the service. So these are the times between each pair in minutes. You want to find the best assignment plan that minimizes the total time. So you see it's 5 by 5, it's one-on-one, and therefore it's a classic assignment problem, and it has nothing to do with assigning workers to jobs. So when solving the problem here, I use the rectangular. You know what? It's 5 by 5. So if I did not do it rectangular, I'll have to have 25 variables. I didn't want to do that. Too many. So I did it here. Look how compact and small and nice it is. And I used the same technique that I did in this problem here. Same technique. And I got the optimal solution here. And it turned out to be 55 minutes total time of transportation inside this warehouse, every half an hour. So then I came up with a question B. I'll let you solve it yourself, although there is a solution, but question B says the following. Management contemplates now introducing a new technology. And you know what, guys? In the real world, it's done all the time. New technologies keep coming and management is offered with improvement, and they know that they have to do it because of competition. They have to keep up with the pace. So now they have an offer to install new technology to the inspection centers here, such that an inspection center can deal with two assembly lines, because you can switch from one device to another device very fast, and then they can get a delivery from assembly line A and switch immediately to B once finished. So it's not a problem. Now, each inspection center can provide two services. And the question is then in which inspection center to do that. The installation of the technology will be in all of them, but which one to use in order to minimize the total time now that you can offer two services. I'll let you solve the problem yourself. It becomes unbalanced and you'll have to see how to get the new assignment plan when it is unbalanced on one side. So instead of once, you'll have two here. But you'll have to correct the problem. You have an example from the previous previous problem, solve it, and you should find 9 minutes of saving. So I thought and made the question as follows. If you have some 9 minutes of saving, can you recover your $15,000 investment in the new technology in 1 year of saving? And you know what it cost you now. $112,000 is the equivalent of 55 minutes every half an hour. When they did the accounting, came up with this amount per year, minimum cost that they can achieve. Now, with the $15,000 invested, maybe they can save money. Question is, can they recover this saving in 1 year? You will see the solution. What you need to do is to solve this problem for when it is unbalanced. That's what I'm asking that you will do. For next time, I'll go back to the transportation. I'll use this file. I'll edit items here. See, I added items that you didn't have before. And I added something here. So I want to work on that only for 10 minutes. You don't need me to do more than 10 minutes here. If you start working on those problems yourself, okay? Yes, there's a shortage problem here. And that's all what I want to do on transportation. And then I'll take another problem on linear programming and do the formulation and do the sensitivity analysis. And this will be our review. Remind you, you have to also get ready for the inventory quantity discount model. And that's all for today. And thank you guys. And I want to close the meeting because I need to close it if I want to stop the recording. If you have questions to me, email to me because I have to close right now.